All right, we're back. Let's take a look at this one. This is a nice little problem too, and I've titled this 3 Easy Pieces because it's based on Feynman's famous book, well, that somebody wrote for Feynman. I've got my back turned to you, and I apologize because I'm looking for it. I got it on my shelf here, called six Easy Pieces in Physics, which are not easy, but that's what he got. But they're relatively straightforward. So are these. So what do we have here? We've got a merry-go-round, which is a solid disc going, and we've got a child of 18 kilograms jumps on board. All right. So what's going to happen to the merry-go-round? It'll slow down, right? Okay. So and the child gets on at the very edge, I think, because they don't give us any new. So it's got a radius of 1.9 meters. So let's do all the work. This is the angular momentum is going to be the same. So let's set up all the algebra, and then let's just crunch the numbers because we got one thing to do here. Okay. So here's the theory behind it. Here's what we're doing. So watch. This is basically I naught omega naught, and this is homework number 11, problem 4. All right, equal I final omega final. Easy peasy. All right. So what are we after? Omega final. Well, it looks like if I can find out what this guy is, and this guy is, and this guy is, and divide them, I'm done. And you are correct. So I naught is equal to, since it's a solid disk, 1/2 mr squared. Okay? Since it's a solid disk, that's 1/2 mr squared. And that's the mass of the merry-go-round, mgr. Okay? And since the child is a blob, all right, the eye of the child, as opposed to the eye of the tiger, the moment of inertia of the child is equal to, now the moment of the inertia of the child is not I final. It's not the moment of inertia final. In other words, we're going to add these two together. Is just mr squared, mc, mass of the child, times r squared. Since r's are the same, so this is nice. So the r's wind up to be the same. So therefore, I final is just I naught plus I of the child. Okay? And they wanted the answer in radians per second when we got done. So here's what we'll do. We'll say I naught times omega naught is equal to I naught plus I of the child times omega final. We'll find omega. We'll go ahead and do this in revolutions per second. Then we'll go ahead and finish it, and then we'll convert to radians. Okay. And so what do I have? I've got I naught omega naught divided by I naught of the child plus I of the child, and then that equals omega final, and then we'll convert to radians per second, and we're done. The rest is just punching in on the calculator. All right, and so let's do it. Let me get down to brass tacks here. 120, 118.44, and 1.9. So mass merry-go-round, mgr, go round, merry-go-round is 120 kilograms. Mass of the child is 18 kilograms, and omega initial is 0.44 revolutions per second, and r is equal to 1.9. Okay? So without further ado, I guess I could pause. I should probably pause this, but I don't want to. So upstairs here, so I naught is equal to 0.5. Let's clear all this stuff. 0.5 times 120 times r, which is 1.9 squared. 217. Let's go with 217 kilograms meters squared. What's the I of the child? He's just a blob, so he's mr squared. and he's 18 times 1.9 squared, 65 kilograms per meter squared. Oh, I've got you, you're not watching me. So when I add these two together, I get 217 plus 65 is equal to 282 kilograms meter squared. And so there we go. I've got 217 times 0.44 over 282 is equal to omega final. This makes sense to me because it's smaller. It's 0.3385 revolutions per second. Now, how many radians are in one revolution? Well, 2 pi. Let's multiply that answer by 2 pi. And I might have made a mistake here somewhere, and that's 2.3 radians per second. That's what I'm going to say the answer is to that. If it's wrong, I have to do it over, and I'll start swearing. 2.13. Let me click in here. 2.13. Submit. Boom. Thought so. Okay, so we're done with that one. So